Done with part one, right? Okay, I even let you out just a little bit early. Anyway. So in chemistry, we do a lot with numbers. Measuring is important. So we need to talk about how we handle those numbers. And before that, then we need to talk about measurements in general. Measurements are done, this is where the little video comes in. You always have to go back to a standard. I like to think of like years ago when they came up with the concept of a foot. So it was like a person's foot. So whose foot did you go by? Okay, but these days it's really very standardized. So if you're talking mass, I like to think if you're talking mass, you're kind of talking the number of atoms that you have crammed in there. What the physicist would say is that not only are you counting how much the mass of those atoms, but also more subatomically, you're counting kind of the mass of the neutrons and the protons, because electrons don't bring those mass. Length is the distance between 2 points. Volume we're going to see actually is kind of linked back to length. But volume is like how much space something occupies. Now we'll have a whole unit on what we call thermodynamics. And temperature is not the same thing as thermal heat. But what temperature will do, like this says, is tell you what direction heat will flow. So if I put up, we'll kind of give you a little precursor. If I put it up an H for hot and a C for cold, do you think that energy will flow from hot to cold or from cold to hot? How many people think it'll flow from hot to cold? Come on, put up your hand. It goes from hot to cold. That's right. And one of the things, didn't we talk about the fact that all matter is in motion? And the hotter something is, the more motion it has. So I'll go ahead and kind of show with arrows. The length of the arrow is a lot of motion, and these little atoms over here are just kind of little chill. They're cold. I think it's had too many knocks. Okay, but yeah, temperature is not thermal energy. But temperature is an indicator of how much thermal energy the object has. Also, in this sense, it will tell the direction that thermal energy go. All right. So we need standards how to measure those three different things that we might want to measure in the chemistry lab. The standard for mass, actually, and I have a picture of a faux standard coming up. You're like, how fake could that be? But you need to go back to worldwide now. We need to be all on the same page what a kilogram is. Okay? If you're going to do trade based upon this mass. You're going to make discoveries based upon this mass. So, and that mass is actually located in Paris, France. Going back to the whole mass standard thing, actually, how do I say this? It's a little bit in transition. They're wanting to kind of get away from this physical object being a standard 1 kilogram, and that's because it actually is not entirely unstable. So, more on that. Length, I said, is the distance between 2 points. Now, one of the things that we can do if we know the speed of an object, we can use time to get to distance. But light, in fact, all forms of electromagnetic radiation, we just talked about this in astronomy, like radio waves and X-rays, they all travel through space that's a vacuum at its particular speed. So we can use light getting from point A to point B, use the time to know that distance. All right, so volume kind of goes back to length a little bit. I've got a picture, and I didn't bring my yardstick today, but if you picture a yardstick, a meter is a little bit longer than a yardstick, okay? And so this would be 1 meter, okay, times 1 meter times 1 meter. So that's a big honking volume, 1 cubic meter. All right, time. Well, one of the things we're going to talk about are the atom. The atom has, what's the circular end? What's the middle of the atom? Nucleus, very good. And in the nucleus, 3 little piggies or something. So what are the 2 things in the nucleus? Protons and neutrons, exactly. So that leaves what's outside the nucleus? Electrons. Very good. Yeah, electrons. And I mention that because, of course, cesium is an element. There, okay, there's cesium. And neutral cesium atom will have 55 protons, 55 electrons. And those electrons, especially the outermost electrons, can what we say transition, okay? And that actually will give a certain amount of energy and a certain amount of time. So anyway, temperature. Now, if you're like, I've seen 273 before. I know I've seen 273 before with regard to temperature. And here's where you've seen it. Celsius, of course, Fahrenheit's totally out the door when it comes to science. We don't use temperature, the Fahrenheit scale at all. But in terms of the Celsius scale and the Kelvin scale, okay, temperature scale, they differ by a factor of 273.15. Now let's see to concentrate. Absolute zero is as cold as it can be, and that corresponds to negative 273.15 degrees Celsius. This is absolute zero. So it must be, you take the Kelvin temperature, and from that you subtract 273.15 units, and that will give you the Celsius temperature. It is so cool, no pun intended, but like they're the same, they're just offset. And this triple point of water, like, what's triple point of water? Well, that's 0 Celsius. That is so cool too. Anyway, our thermometers can be calibrated actually using something kind of handy in the lab. Amount. So we talk about it. If I was to ask you how many eggs you have in the refrigerator, you might talk in terms of a dozen. If I were to ask you about pencils, a lot of times they come in terms of a gross. That's 144 12. But when it comes to atoms and molecules, you know, they're very small. So we instead then talk about amount in terms of a mole. Does anybody remember 1 mole is equal to how many? 6.022 times 10 to the 23rd. Sometimes I have to double check, but yeah, that's the definition of a mole. Yeah, 6.022, very good, times 10 to the 23rd. And so if you have 12 grams of carbon, the specific isotopic form of carbon, carbon 12, then you have 6.022 times 10 to the 23rd. Cute little carbon atoms. Okay. So in chemistry, we can't talk in terms of dozens or gross. We got to take it up a notch. That's the mole. So here's the video I was going to show you. So this is the fake. This is the one in Paris. Remember that iridium piece of metal? That's exactly 1 kilogram. It is amazing. I can almost picture them doing this. So what they do is they have this prime standard, okay? And then what they do is they basically make little babies, first generation from that, okay? And then they make little babies from that, okay? And these are like things that can go out in the world and make sure your scales are doing what they're supposed to do. Calibrate your scales. So I thought I'd give a little plug to NIST, National Institute of Standards. Almost like these weights. And when I worked in the lab at the ignition plant, the weights that you get to calibrate your scales have a pedigree. And the pedigree goes back to something that the whole world is looking at. So that's cool. So the length is the distance between 2 points. Of course, we're most familiar with the English system, but we definitely need to kind of switch gears to the metric system with regard to length. And I'm going to show you which metric prefixes you can get on. The length between the English and the metric system, English inches and metric centimeters, you're going to see that that's called an equivalency statement. 1 inch is equal to 2.54 centimeters. That actually is something that you're going to need to commit to memory. So I'll remind you of that coming up. That's an exact relationship. It's what we say by definition. This is not an exact relationship between, I told you that meter stick is a little bit longer than a yardstick. Okay. So this actually would be a cubic meter, like 1 meter cubed. Well, what does that mean? Well, we can get the volume of anything by taking a cube like this, taking its length times its width times its height. In the case of 1 cubic meter, all three sides are 1 meter. Okay, so, and this is, we don't use much with the deci prefix. Okay, centi, yes, deci, not so much, milli, yes. But 1 cubic decimeter is equal to 1 liter. What we do care about, kind of the length cubed versus what's happening with regard to liters, is this important relationship up here. 1 centimeter cubed, like you take a centimeter and you make a box out of it, centimeter, 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 length, width, and height. Then the volume that's contained by that kilo cube is 1 milliliter. That equivalency statement, that is another exact relationship. That actually comes not by, well, it comes by definition. This is one of the strangest, does anybody else find it strange? You expect, and this is an author's image, and I was like, well, maybe it's 2 images and I just need to, it's 1 image. What kind of throws me off is they're saying that this is that 1 cubic centimeter. So we have length, width, and height are all 1 centimeter. So if you take 1 centimeter times 1 centimeter, the number is 1, the units are centimeters raised to the 3rd power. I get that. But look, if that's 1 centimeter, and that's, I guess to me, this looks, maybe it's an optical illusion, maybe I'm wrong. But this looks similar to 1, not 1.8. I guess it does. Gotta look at it. This, I don't know. I'm thinking that almost looks like 1 centimeter, 1.8. Anyway, that's not the point. When we checked into lab, we said that on glassware, a lot of times you'll have these white gradation marks, okay? And I think I might have said that like this beaker, you know, you could get 100 milliliters in this, let's go with 50. You could get 50 milliliters in this beaker and you go, let's see, 20, 30, 40. Yes, I guess you go right there. It's pretty rough. You could get 50 milliliters in here in this graduated cylinder, and that's better. You could have do you guys remember what the name of this is? Pipette, very good. You could have a pipette, and I think I've got one, that has a capacity of 50 milliliters. It's kind of big. And that would be even better than this. This is called a volumetric flask, and this is called a burette. You guys will be using burettes this semester. A burette works by basically dripping liquid out the end here, and there's a little stopcock to let stuff go down. And the gradations on a burette are kind of backwards. It's 0 at the top, and it kind of. All right. So in the SI system stands for international. So worldwide, we come up with these base units. One of the things right off the bat that might surprise you, well, one thing that doesn't surprise you is their metric, right? Okay, so for length we have meters. One of the things that I think is kind of surprising is instead of grams per mass, we have kilograms. I blame the physics people. For time it's seconds, temperature it's Kelvin, units of Kelvin, current ampere, mole amount, luminosity, candles. So in OpenStax is this table right here. So this is 1.3. So you're going to need to know these metric prefixes. Oh, serious. Now what I usually tell students, and I think it's worked in the past, so I'll go ahead and tell you this, is the ones you need to memorize. There's only about 4 you need to memorize. To do problems, you're going to have to know all of them. But the 4 you're going to need to come to a test look like this. They are centi, milli, micro, so 3 small ones, and then 1 big one, the kilo. I think those 4 will probably get you down the road in this class with regard to an exam. Not to say you don't have to wrestle with the other ones. Now in this class, I'm already assuming that we're all on the same page with regard to scientific notation. You see these here, 10 raised to a power. I like to think of that column as being 1 times 10 raised to a power, because just 10 raised to a power kind of drives me nuts. So this is how this works. If I wanted to focus on milli, okay, anytime you see the milli prefix, okay, milli means 1 times 10 to the negative 3rd. That's what milli means. So that means if we pick on, for instance, meters, millimeters, we could say that 1 millimeter is equal to 1 times 10 to the negative third meters. That's how that works. 1 millimeter is equal to, I have to concentrate, make sure I get this right. 1 millimeter is equal to 1 times 10 to the negative third meters. Just for kicks, before I go on to the next slide, are we all on this same page? That I could take 1 times 10 to the negative third, and it's the same thing as this. You guys good with that? 1.001, awesome. One more thing, if I want to put it in a fraction, which you're going to see here in a minute, that would be 1/1000. They all mean the same thing. So know those. And then the table in your textbook also has this last column, which kind of picks a particular something, like I picked meters, and kind of shows you an equivalency statement. How that makes sense. Very good. This is a table that I used to have in my old textbook. Feel free to go ahead and mark, what did I say, centi, milli, micro, and the one that's larger, kilo. Those 4. So picking on the prefix centi and the unit of measurement meter, we could say that 1 centimeter is equal to 1/100th of a meter, because the prefix for centi is 10 to the minus second. Right? And again, we're going to be talking about these. It's like these are called equivalency statements. And as I hold my hands up like this, I'm trying to be like one of those hand balances. And right here in the middle is an equal sign. So that's why I do that. Sue's like, why are you doing that? These are equivalency statements. These happen to be actually an exact equivalence statement. Okay. So there's that. Now I'm going to do something a little bit of, it's not magic at all, but I don't like fractions like this. So this slide's going to kind of show you at the bottom another way to look at the relationship between a centimeter and a meter. One of the things you know in algebra is that you can multiply both sides of the equivalency statement by the same thing and you haven't messed anything up, right? You still have equality on both sides. So all I'm doing is taking 100 times both sides. Notice right here, these two hundreds are actually, the 100 in the numerator and the 100 in the denominator are going to cancel each other out. So I could rewrite that and I could say that 100 centimeters is equal to 1 meter. Okay. So honestly, both things in the blue box are great, perfect relationships between a centimeter and a meter. I mention this because you're going to see me when I work problems. A lot of times I will go for this one right here just because I don't have fractions. Be careful though. You're in good shape if you put 100 meters is equal to 1 centimeter. I see that all the time. So you've got to take one more look at it. Does 100 meters equal 1 centimeter? No. But are there 100 centimeters in 1 meter? Yes. Okay. So you're in very good company, but you gotta, a lot of times if you make that mistake in an inequality statement that you're going to use in your problem, you'll see it in the end. You'll be like, oh, something's not right here. So sometimes chemistry problems are kind of like, but they're not linear. They're not like you go to the kitchen and make you mac and cheese. They're more like a piece of art where you kind of put it together, you like fix something, and you know, that's what they are. Here are some more equality statements. I'll put an arrow next to the one you need to commit to memory. So my arrows are memorized. So the only one you need to memorize is the one I mentioned actually earlier. With regard to length in the English and metric system, by definition, there's this awesome relationship between inches and centimeters. Now, again, is it possible, and I've done it before, to accidentally mix the two? like the number with the units, do I sometimes accidentally say that 1 centimeter is exactly equal to 2.54 inches? I do. Is that wrong? Yes. Okay, do I catch myself? Usually. You know, you're gonna, if you kind of picture a centimeter and you're like 2.54 inches, that doesn't quite seem right. So anyway, the other two are approximate, between the English and metric system with regard to volume and mass. Put another way, if you need these two on a test, I will give them to you. Okay? Not the first one. The last two I will give to you. Again, arrow, memorize. I think this is so cool. So this is within the metric system, right? It's an important link between the whole liter thing and the meter thing. By definition, 1 milliliter is exactly equal to 1 centimeter cubed, 1 cubic centimeter. Of course, in the you guys have seen this if you've had the misfortune of visiting people in the hospital or something. Centimeter cubed is the same thing as cc. But don't they also do that like in cars and something like that? Like fuel?
Batteries.
Okay, batteries. Okay. So cc is the same thing as centimeter cubed. Thank you. So you're probably kind of familiar with this whole thing. It is case sensitive. So the only uppercase letter you get to use is liters. Excuse me, capital L. Speaking of, and again, well, I don't know if I do this, make this mistake anymore. But with regard to your units, you know, capitalize the L, but don't capitalize anything else, unless it's a, nope, don't capitalize anything else. Don't put a period there. Oh, I know, a common thing is, and once I put it, you're like, oh, a common thing, of course, the abbreviation for grams is G. It's not GM, okay? And it's not GM period, okay? Nope, it's simply G. The other thing is we don't include the S, like if it's 2.54 centimeters, we don't put 2.54 CMS. Okay, so I know you're like, well, I wouldn't do that, but so in chemistry, we need to talk numbers. We need to talk quantities. In life, we need to talk numbers and quantities. I like that little video we watched because it kind of, this video, it gives you an inkling of, you know, dude, measurements are all around us. So when it comes time for measurement, there's two ways to kind of say how good that measurement was. There is the accuracy of that measurement, how close it was to a true value. Sometimes the true value is more obvious than others, okay? Then there is the precision. I think of precision as scatter. And precision can only be measured if you do the measurement, can only be assessed if you do the measurement multiple times. Do the measurement several times and see how close you get to the same number. You'd be like, why wouldn't I get the same number? And if you've dabbled in a lab, any sort of lab, for any time at all, you're like, I know why I don't get the same number. There's always scatter in, that's just the way it goes. Okay. So we can kind of look at accuracy and precision in terms of a dartboard. Anybody here throw darts? Yeah. So the true value in throwing darts would be the bullseye, right? So here we have an example of where these are multiple darts. I don't know if you kind of see a little bit scattered. So notice that they hit the target, so they're accurate. And dude, this guy is right on. Reproducibility is great. Okay, so precision's great. Well, not quite hitting the bullseye. So accuracy, not so much. But is it nice and tight? Yeah. Low accuracy, high precision. All right. Then we have this scenario. where you can see they're even farther from the bullseye, okay, and they even have more of a scatter. So farther from the bullseye, accuracy went down, more of a scatter, precision also went down. One of the, it's not a game actually, but like for labs who do outside work, they actually oftentimes have to, I don't know how often, but they get sent blind samples to run. So someone knows the values, but they're just getting, it's like a test for the lab. And so when they do that, the people who assess how well they did will be looking at their accuracy and their precision. And then when that lab, if they are do outside samples, they always have to present to their customer how accurate and how precise they were on that particular analysis. I would argue there's one more scenario. Let's say he or she threw 5 darts, and here's the 5 darts. I don't know if you see that red there. But to me, the precision sucks. Precision's terrible. But to me, if you take an average of those, you know, accuracy not so bad. Oh, anyway. All right. So if you know the true value, and again, you may not always know the true value. Many of the experiments we're going to be doing this semester, you guys are going to be doing in the lab. You'll be shooting it for a particular target, like a physical property, a constant or something. But if you know what the true value is going to be, then you can assess what you got with what the true value is, and then that's what we call your error. That's, you know, that's your error. So an error is how far you are from the true value. Uncertainty is kind of the spread. Uncertainty is back to precision. How reproducible or unreproducible are you? Okay. So error, how far are you from the real answer? Absolute error is the easiest. Let's just say you knew a length. Let's just say you knew the boiling point temperature of water was 100.00 at this particular atmospheric pressure. And let's say you ran it experimentally and you got 98.0 degrees Celsius. Your error is 2.0 degrees Celsius. Okay? So that's pretty easy. That's your absolute error. Well, then there is something called relative error. Let's do the example we just did. There'll be times when what relative error is takes into consideration how big of a value was it, basically. So all you got to do for relative error is take your absolute error, which is theoretical minus actual. So in our case, it was the 100.0 degrees Celsius minus 98.0 degrees Celsius. Okay, divided by the actual value, 100.0 degrees Celsius, times a percent, and that is your relative error. So what is that? That's 2%. 2% error. So that's how that works. Okay, where this was your actual. This is your experimental, and this is your actual. We're going to go on to the next part too. So the fact that you guys are handing in, that's good. So we're all kind of on the same page with that. So, and I did bring mine. Now what's going to be due next time we meet will be dun 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 part 2. Let's do Wednesday. We're going to take a look at lecture slides for part 3 though. Don't forget, like, the answers are already posted. I did some changing around in Canvas. You actually can have the answers in Canvas, which is kind of weird, but I like it. Okay, let's see. Still talking numbers here. Part 3. Significant figures, the bane of our existence. No, I'm going to kind of roll out something that's going to be applied for the rest of the semester. And I'll just cut to the chase. It's how do you round your answer? Like if you put a couple numbers in the calculator, how do you round your answer? It actually comes back to what you're allowed to round your answer to. So I use the phrase "thou shalt not lie." Let's say you do kind of an awesome sort of chemistry problems are very, very pretty. I think once you lay them out, they're very pretty. They're almost like artwork. So you do all this kind of multiplying, subtracting, adding, and your calculator gives you the answer. Okay, you have to round that answer according to kind of what you inputted into it. Okay. I'll talk to you about that. So this is all measured values. Now I'm actually going to have that's a little bit of a lie. Not all measured quantities have uncertainty with them. The ones that don't have uncertainty are very special cases. But for instance, if I measure this marker and I'm like, oh, this is maybe 5.39 inches. Well, I stopped in the hundredths place, 5.39. Did I mean it was 5.39 plus or minus 0.01 inches? I mean, there's always a little bit of uncertainty in that sort of measurement. Okay. When I tell somebody I'm going to see them in an hour and a half, do I mean an hour and a half plus or minus 5 minutes? There's a little bit of wiggle in all of that. Do I mean it right on the nose? An hour and a half? 90 minutes? Do I mean it? There's uncertainty in that measurement. There is. Miss knows it. We know it. You know it. Okay. There's uncertainty in all. I say there's a few exceptions, but on most major quantities, there's definitely uncertainty. So when we go ahead, for instance, what did I say? 3.49.
You said 5.49.
5.49 inches. 5.49 inches. Usually, and I think of it as like a tolerance. Usually, what I meant is in this last digit, I'm at plus or minus 1. Okay, that's the play. Not always. I don't know if you remember Thursday when you checked in and I held up that pipette, and the tolerance for Zach was plus or minus 0.04. Okay, but unless it's stated, so there's a little bit of wiggle there. It's just life. Okay. So this whole bit about rounding, okay, this whole bit about, remember, working that complex chemistry problem and giving an answer that reflects sort of that uncertainty in the values you use to calculate that answer. It's important, for instance, like if I was going back to this marker and I said it's 5.49 inches, well, what if I told somebody it was 5.49327654 inches? You'd be like, all right, Mrs. Snipes. You know, 0.1. What kind of measuring device are you using? So just to kind of give you an idea why we do this. Now, as we get going, I'm going to use this as an example, and this will make more sense to you in a minute. But I like to put, well, this is right. Okay, yeah. Uncertain digit will always be the last digit in the value. So let me grab a red here. We got time. This is so nice for somebody to bring these in. So I like to put a question mark over the digit where the uncertainty is. There's a question mark. And thus kind of goes. And yeah. But you're only allowed one uncertain digit, and it will be your rightmost. Get my left and right side. Okay, so here we go. Somebody measured something. I don't have any units, but assuming that this is a measurement, it could be centimeters or feet or liters. 4.1267, and 7 is the question mark. 7 is the uncertain digit. So we'd say plus or minus 0.0001 units, unless they said otherwise. Here's a look at kind of this. I like this slide. I was getting ready for lecture. I'm like, oh, that is so cool, because this is what you guys need to do in lab. So listen up. You guys will be definitely dealing with volumes. Of course, what's the name of this piece of glassware? Graduated cylinder, very good. You might say, let's see, it looks like gradations are every what, 1? Yeah, 1 milliliter. You might say, well, that looks like it's close to the 22. You might say it's 22 milliliters. Okay? But what I need you to do is to, just like this slide says, okay, the gradations are every 1 milliliter. And best practices, what you'll do this semester is kind of estimate, basically take those gradations and split them in units of 10. Split them in 10 units. Okay, so if we split this in 10 units, it looks like it might be, this guy, the author said, maybe 6 units between, you know, say like 6 dots between the 21 and the 22. So you guys are gonna have to do that. And I think I used the word meniscus the other day. Meniscus is kind of the shape that it's kind of forming, and you take the bottom of that. So 21.6 millimeters. So 20, I'm hoping you're kind of seeing in this little kind of discussion that we are relaying 2 different things. If we say 22 is not equal to 21.6, I should use units. Those relay 2 different things. Sometimes students are like, that's close enough to 22. You'd round 21.6 up to 22. It's not the same number. And when you go to use that volume in a calculation, which you might often do, then it's going to screw your calculation. Okay, you'll see how that works too. So I said a few slides ago, I feel like that all measured quantities have uncertainty associated with them. I feel like that was a lie, and this is why that was a lie. Because there is a broad group of measurements that give us actually exact numbers with no uncertainty. The 2 types of exact numbers are listed right here. These are 2 types. First type, if you count. Like if I count people in here, including me, I get 8. You know, it's not like we have a half a person here, okay? We're counting people. We have 8 people. Is it a measured quantity? Yeah. Is there any uncertainty? No. The other one is by definition. One of my favorite sort of deals by definition is within the metric system. You know, the milli was set by definition to be 1/1000th by definition of the base unit, milli. So within the metric system, those are all, if you're using an inequality within the metric system, that's all exact too. That's by definition. So when we get talking, and I think I'm probably going to leave it till Wednesday, but on Wednesday, when we start what we say counting significant figures, I'll show you what that looks like. If I were to count significant figures on these things over here, I'm going to put a check mark next to every significant figure. 1, 2, 3. I have 3 significant figures. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a lot of significant figures. 2, 3. Okay, that's all I need. So if you're going to count significant, what did I say, 8 people? 8 people. The number of significant figures there for that number 8 can be thought of as a couple different ways. We can kind of think of it as 8.0000000, an infinite number of zeros. kind of related to that, we can figure, we'll talk about why these are called trailing zeros after the decimal. Trailing zeros after the decimal, these are all going to be significant. So it's an infinite number of significant figures. We'll kind of talk about how that plays into when you're dealing with an exact number in your calculations. How does that make you round your number? Well, that's a good place to stop. If it's okay with you. 5 minutes early again. I know you guys got to slow me down. But, yeah. Let me know if you have any questions. Otherwise, I guess I'll see you on Wednesday.